Okay, I'm logging off. Can you hear me now? 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 I think we're streaming. Good morning. How are you this morning? I'm up and Adam. What about you? Adam. Get it? I'm not Adam, but you are Adam. Yay! Good morning, good morning, good morning. I think today's lecture will be a little bit easier than yesterday's was. Good morning, way to be here, guys. It's bright and early morning, Tuesday morning. So I have an early bird here. See if you can do this early bird, warm your brain up. It says, spin the spinner 100 times. How many times do you expect to win? So start off by doing that early bird. See what you come up with as we wait for everybody to get here. Wait our few minutes for everybody to arrive in class. Yay, we kind of have this routine down now, starting to get into routine. And y'all did a great job yesterday of getting those first 10 done. That was great. And today should go a little faster, hopefully. These 10 should go a little faster. And then you'll be ready to turn in one assignment. Be done with it. Good morning, good morning, good morning. Whew. Do a little stretching. Oh. Get in my stretching routine. Before we start. Hey, Zoe. Good morning. Good morning, good morning. Just a few more minutes here. Make sure everybody's here. Y'all go ahead and do this early bird. Spin the spinner 100 times. How many times do you expect to win? How many times do you expect to win? Howdy, 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 howdy ho, howdy ho. Whew. Started a little earlier today. Well, not really. Good morning, good morning. Starting to join. Y'all have all subscribed to us so you get a little notification now when I come live. Is that how that works? I'm on the opposite end, so I'm not quite sure how it works from y'all's end, how you find me in the mornings. But somehow or another, it's working out. And you're able to get here to the Simpson classroom. Just totally took over this room, kicked my daughter out, moved her down to my dad's house so I could have this room. Now I have a whole setup, whole classroom. Yesterday I was teacher in the morning, custodian in the afternoon. Had to clean up my room because it was getting pretty messy. Even have a little gym over here. Y'all can't see it, but got my gym in my classroom now. It's nice. Can write a problem or two, do exercise or two. Maybe I'll get in shape for the first time. I doubt it. Something about lack of sleep. Y'all get this early bird done. Spin the spinner 100 times. How many times do you expect to win? And then my son wrote our haiku for the day. Here's our haiku for the day. As the flowers bloom and the beams of daylight shine, I hide in my room. That's how we all feel right now, right? There's things going on outside. The flowers are blooming and it's beautiful outside. Well, yesterday it was kind of nasty, that rain going on. But it's beautiful outside, and then here we are hiding in our houses. I mean, this is us on a normal basis, though. So now that we're having to hide in our rooms, if this is what we normally do, and now we're, because we're having to, we start to realize, oh, there are birds outside and flowers. Maybe I should go out and enjoy them. It's still okay to go out and do those things. You just don't want to be, 6 feet from anyone. So I think my daughter and my dad today are planning on going for a picnic in the park. They're going to take their chairs and a little table to the park, and they're just going to have a little picnic in the park, and they're going to stay away from everybody else. So that still can be done. You can still go enjoy yourself. Take some wipes with you and wipe down if you touch anything before you touch your face. And just don't touch anything. That'd probably be best. But outings are okay. So hopefully that goes well today. All right. So I feel like we've got class going on. Several of you have arrived. And here's our early bird for the morning. We've got spin the spinner 100 times. How many times do you expect to win? Eve, you and I were up too late. But way to be here this morning again after being here. You have like 2 seconds. Get on it, Bo. You got it's almost 9, it's past 9:30. So y'all get, oh, look. 25 out of 100. So, how'd you know that, Priscilla? What's going on? So, how many times do I expect to win? My marker's up here. Let's use this marker. You're right. If this is a fourth of my, this win is a fourth of my spinner. So I expect to win a fourth of the time. So I like that, or you could even call a fourth 25%, right? So if I'm doing it 100 times and I expect to win 25% of the times, or a fourth of the times, I like that 25 times. So we expect to do, a fourth times 100, a fourth of the time, or 25 times. Or maybe you just said, well, that's 25% of 100, which again is 25 times. So we expect to win there 25 times. And this is, so let's think about what this means. That's what we expect to happen. It doesn't mean that it actually will happen. So for instance, yeah, that's exactly right. Our P here would be 25, or 1/4, and our Q then would be 3/4. So if I expect to win 25 times, how many times would I expect to lose then? Yeah, and notice that I'm not going to expect to win a fraction. I'm going to expect to win 25 times. Notice I'm getting out a whole number. Notice that how many times I get out a whole number. But when I ask what is the probability, then I get out a fraction. So if I asked you what's the probability, then you would give me that 25 over 100, or 1/4 would be the probability. Good, and Carrie, yeah, I would do 75 times. That's right. Good, Bo and Monty, good. Y'all got this. So that's what I would expect to lose then 75 times. Now, it doesn't mean it will happen. That's my expectation. But, if I'm spinning it, I'm probably going to lose every single time. That's just how my luck works. It just happens that way. Whereas, if Eve spins it, maybe she wins every time. Maybe she wins all 100 times. So in each one of us, if we go around and spin it 100 times, then what this 25 is on average, we should get 25. In other words, if Bo spins it 100 times, and maybe he wins 30 times, and Amani spins it 100 times, maybe she wins 20 times, and Brandy spins it 100 times, and maybe she wins 25 times. And Kara spins it 100 times, and she wins 35 times. And Priscilla spins it 100 times, and she wins 25 times. I'm going to take all those winnings of 20 and 25 and 30 and 35, and I'm going to add them together and divide. I'm going to find the mean, or the average of those. That average should turn out to be 25. That's what this expectation is we expect to win on average 25 times. So today we're going to talk about our expected value, our expectation, and that's all that is it's just an average. So let me put that down. Expected value. When I talk about the expected value, I'm really just talking about on average. Now, when I say on average, what are y'all supposed to ask me? That's the thing, is what am I supposed to ask? What are you supposed to ask me when I say on average? So, which average am I talking about? And on this, I mean on the mean average. I'm talking about the mean. So on average, how many times do I get it? And I'm talking about the mean. Good. That's exactly what you're supposed to ask. So that's the expected value is on average, how many do I expect? And notice how we got that mean. By the way, I denote the expected value. You remember that mu symbol? The mu symbol was just the mean. Well, when I talk about my expected value, because it is just a mean, I use the mu symbol also to represent the expected value. And for binomials, finding this average is super easy. Notice what we did to find the average number of times we would spin it. All we did here was take the probability for success, the 1/4, you told me that was your P, your probability for success, and you multiplied it times your 100. Maybe I should back up and make sure that this is binomial. Is this actually binomial? Do I have two outcomes? Yeah, I've got a win and a lose. Those are two outcomes. Do I have a fixed number of trials? Yes, I'm spinning it 100 times. And does the probability remain the same every single time? Oh yeah, look, it stays 1/4 every single time, so it is binomial. And for this binomial, in order to find that average, or the expected amount, I just took the probability for success and multiplied it times the number of trials. So our expected value formula for binomial is nice and simple. Binomial expected value is just the number of trials times the probability of success. That's all it is. So let me change this for just a second. Instead of spinning the spinner of 100 times, let's do this. I want you to spin the spinner 48 times. What's the expected value of that experiment? What is the expected value of that experiment? If I do it 48 times, what's the expected value? Well, all I'm going to do is take my number of trials. So in this case, all I did was change that 100 to 48. And then I multiply it times my probability for success of 1/4, because success here is 1/4. And I end up with 12. So here I expect to get 12 wins. That's my expected value when I spin that spinner 48 times. Okay, now, do you remember standard deviation? Remember how we found standard deviation before? How we had that table? We put our x values, and then we had to find the distance from the mean, and then we had to find we had to square all those values, add them up and divide. Do you remember that complication? Hey, well, it turns out for binomial, it's so much easier. It's so much easier for standard deviation for the binomial. So if I want to find out how much this game varies, does it vary a lot? How much variability is there? What is the variance? What we do to find the variance of a binomial and remember the symbol for variance, that all we do is do the sigma squared. Remember that's variance. This is variance. Maybe you remember that. It's been a whole 2 spring breaks and a long time ago. So good. I'm glad y'all remember. That was a long time ago. So now for the variance there, we're going to do for binomial. It's just n times p times. So notice that's just the expected value. This is the same thing as that expected value. I could write it this way, or I could write it that way. Times q. So times the probability for failure. Try it, little sigma. That's exactly right. So what would the variance of this particular one be? If my variance is just the mean times that probability of failure. And Kara told us earlier what our Q was. She told us what our probability for failure was. So to find that variance, I'm just going to take and do this mean. So to find the variance, I'm just going to take my n times my p and then multiply that times my q, which Ann Kara told us was 3/4. It is going to be easier than yesterday's. Today's going to be a lot faster than yesterday's. See, so far it's not too bad, right? To find the expected value, you just do n times p, and then to find the variance, you just multiply it times q. Okay, so here, if I multiply that 12 times 3/4, put that 12 over 1, I'm going to go ahead and divide first so that I get 3 there. 4 goes into 12 3 times. Now I multiply straight across and I get 9. So the variance here is 9. Now, what is the standard deviation of it? Maybe you remember standard deviation, maybe not. But here it's a lot easier than it was before. But this is the same. Once I have the variance, how did I get the standard deviation? Remember, standard deviation was just that little sigma without the squared. So here's my standard deviation. And the way I get that is I just take my variance and take the square root of it. The square root of that variance. Or you could say the square root of the mean times your probability for failure. Or you could say the square root of n times p, because that's all mu is n times p times q. You know, all these things mean the same thing. Once I do my n times my p, I have my mu, my expected value. And then once I have my expected value times my probability for failure, then I have my variance, take the square root of that, and I've got my standard deviation. So back over here, if I want to find the standard deviation of this, all I do is take the square root of 9, and I end up with 3. So the standard deviation is 3. My variance is 9, and my expected value, or the mean, is 12. Okay, now how in the world do we use all this? All right, let me erase this. I'm going to put these things over here just to help us remember. So today we're going to use this. We're going to use our mu, our expected value is n times p. Our variance is just that mu times q, and then our standard deviation is just going to be the square root of that variance. Okay, so I'm going to erase all this, and I'm going to show you how do we use this. Well, let's back up and remind ourselves about Chebyshevs. What do you remember about Chebyshev? Do you remember Chebyshevs? I know, all this was so long ago. That was back, 2 spring breaks and a long time ago. That's it. You got it. Hey, look, Amani was already leading me there. That's exactly right. That we're going to use that Chebyshevs. So you remember Chebyshevs? You remember that Chebyshev tells me that for that 75% of my data is within 2 standard deviations of the mean. You remember that? And then what about 3 standard deviations from the mean? You remember what that was? I think it was 88.9%. Is that right? 88.9% is within 3. And remember, I'm forgetting 2 words on there that are super important, because it's at least 75% of the data, or at least 88.9% is within 3 standard deviations from the mean. Okay, so how do we use this? Well, I know my mean here is 12. I know my mean is 12. So if I go up 1 standard deviation, so on average, we're going to get 12. Correct. But 1 standard deviation is 15. Remember, you just add that 3 to both sides. And then add another 3 to it, and you get 18. So 2 standard deviations up is 18. Now I'm going to go back 2 standard deviations. So that I've got 11. That's not right. Subtract 3 from that. Subtract 3 from that. 9. 12 minus 3 is 9. I don't know how I came up with 11. And subtract 3 from that. I'm just going down that standard deviation, and I'm at 6. So this is 2 standard deviations below the mean. And 75% of the time, we should get between 6 and 18 spins. So, if I'm running a booth at a carnival and I'm having kids come and spin the spinner 48 times for some reason, then I would expect 75% of the time for them to win between 6 and 18 times. That would be the expectation for that to happen. Zoe, I'm counting up and down by 3 because my standard deviation is 3. So I'm adding 3 each time because this is up 1 standard deviation. Add another 3 and I've got 2 standard deviations. And the same thing back. If I go back 3, I'm going backwards a standard deviation. So it's just that distance from the mean. And I know at least 75% of the time I would get between 6 wins and 18 wins. So now go up 1 more standard deviation, 18, 19, 20, 21. And that's 3 standard deviations. Go back another one. I ran out of room. And I'm at 3. That's 3 standard deviations. So I know that at least 88.9% of the time that people are going to win between 3 and 21 times. Now, if something happens and I have 48 people come up one day to spin my spinner to win or lose, 88% of the time, let's say every day, 48 people come up and spin my spinner. Well, I know that I need to have that 88% of the time I'm going to have 3 wins during the day up to 21 wins. But let's say I start having, and it could happen on occasion, I could have something rare happen where I have more than that, because there's, this is just 88.9%. But let's say that over and over again, I start having people spinning more than 21 times, and it just happens over and over and over again. Then all of a sudden, I may be like, wait a minute, something's going on. My spinner's not working correctly, or these guys have figured out a way to spin it so that it lands funny every time. Maybe I got ringers in there that are cheating somehow. So I start looking at those different methods, start looking to see why do we have something weird going on. So I expect for 88.9% of the time there to be 3 to 21 wins. And if it's outside of that, and especially repeatedly, then I start thinking there's something weird going on. Let me check it out. So that's how we use Chebyshev. That's how we use that standard deviation to help us out. So you can see, though, that today, finding our expected value and finding that standard variance and standard deviation isn't going to be too hard. All right, so let's do a couple other examples here. And I have my board ready here with my other examples. I know, Cheaters Eve, why are they doing that? Why would they do that? So, here's a couple of examples. A manufacturing plant produces defects 1% of the time. If the plant produces 1,100,000 parts a day, wow, they're really churning it out, man. Must be some easy part to spit out there. How many defects do we expect to produce? So if we've got 1,100,000, I feel like there's wait a minute. My commas are wrong. No wonder. Let's try that again. How about just 110,000? Oh, that makes more sense. Okay, good. 110,000. Numbers. Oh yeah, 110,000. I like 110,000 better. So 110,000 parts a day. How many defects do we expect to produce? Still a lot. How many defects might we have? Okay, well, first of all, is this binomial? Can we just do that expectation? Well, it kind of makes sense just to multiply the number of trials times that 1%. If 1% of them are defects, I feel like we're just doing some multiplication there, 1% of 110,000. So let's just see if it really does fit that binomial. Are there two outcomes? Well, sure, it's defect or not a defect. And is the probability remain the same for them to be a defect? Yes, it's 1%. And is there a fixed number of trials? Yes, it's that 110,000. And good, Adam, that's exactly it. Y'all have got this. So that all I'm doing to find the expected value is just I'm taking that number of trials times my probability for success. You know, this time a defect is a success, so that's weird. So y'all are doing great. Y'all got those two outcomes. So this is 1%. Remember that 1% is 1 over 100. Or if you're going to put it as a decimal, it's 0.01. I'm going to write it as a decimal just because yesterday when I was helping people with decimals, we were having trouble reading them. So I'm going to write that as a decimal. This is tenths place. So if I have a number in the tenths place, I read it as tenths. This is hundredths place. So when it's out here at the hundredths place, I read it as 1/100ths. And we know that because when we write it as a fraction, we write it as 1 over 100. So it's 1/100th. That's what it looks like as a decimal. We did that at the beginning of class, but I know that's been a long time ago. You could just multiply it that way, but I like to use my fractions because check this out, the zeros and the zeros go away. And so now I'm just multiplying 1 times that, which just gives me that 1,100, like Adam said. So I expect to have 1,100 defects each day. Now, what is the variance? So what's my variance going to be in this particular plan? How much is that going to vary? What's that variance going to be? So for the variance, all I do is I take that that mean, or my n times p there, and I multiply it times my q. So we have to figure out what is our probability for failure. If my probability for success is 1%, what's my probability for failure? So I have that 1,100 is my mean, and then my probability for failure is 99%, because 99% is the complement of 1%. Or I could write that as 1,100 times. As a decimal, it would look like this, 0.99. I would read that as 99 hundredths because it ends in the hundredths place. Or you could do it as times 99 over 100. Again, the 100, divide the top and bottom by 100. And then 99 times 11, well, 9. Add these two together to get 18. Carry 1, 9, 10. So my variance is 1,089. 99% is our probability for failure. It's a little bit weird because you don't think of defects as your probability for success, but you know when I'm talking about what it is I'm looking for, so in this case my defects is my success, and then my failure would be this 99% of being okay. So it's weird, the terminology, but because we were looking for defects, then that's our success. So this is the variance for those defects. Now to find the standard deviation, I just take that and find the square root of it. So I'm just going to take that and find the square root of it to find the standard deviation. Now I know y'all are like at home now and y'all are using calculators, busting those out. I guess it's okay. So I guess find out what that is. I'm gonna do it fancy though. Look, this was 99 times 11. I'm gonna go back to that 99 times 11. 11 times 99. I know that that multiplies to be this. And so then I know that 99, you can just use your calculator to find it. But I'm going to show you without a calculator how I would do this. This 11, notice that 99 breaks up to be 11 times 9. So here I have the square root of 11 times 11 times the square root of 9. Well, the square root of 11 times 11 is just 11. The square root of 9 is just 3. So I bet when you plugged that into your little calculator, you got 33 out. Maybe. See if that's what you got. It's all right. I would plug that in the calculator too. So I might do some estimation to make sure that it made sense when I got my answer out, but I too would use a calculator for a number that big. Okay, so my standard deviation is 33. So here's the question for you. 75% of the time, how many defects should I expect? Between what two numbers? How many defects should I expect? So I'm going to erase this as y'all figure that out. You figure it out. Tell me, 75% of the time, how many defects between what two numbers should I expect? And I'm going to erase this part so I can draw out my number line to help me out. And remember, the way we find that, 75% of the time, at least 75% of the time, I'm looking at two standard deviations out. So I'm going to go start at my 1,100. That's on average. Good, y'all have got this. So you just add that 33 twice, and then subtract that 33 twice. Uh-oh, that part's hard. So you got 1,000, subtract 33, 70, 67. Is that what y'all got? And then subtract another 33 from that, so that you're at 34. So at least 75% of the time, I'm going to expect to get between 1,034 defects and 1,166 defects. So again, if more than 75% of the time I'm getting something out here, I'm getting big numbers, where I'm getting a lot, maybe I'm getting 1,250 defects. That could happen once, it might happen once. But if it's happening over and over and over again, so that 75% of the time it's not between here, then I start looking at my machines and I start saying, where is there a mistake? Or is there one particular person on the line that's helping to make it make too many defects? Or what is it that's happening? Because that's not what I expect to happen. So that's exactly how we use that in statistics. We can find errors in things by looking for those outside that 75% or that 88.9%. So, all right, so there's an example. Let's do this one more example here. So we found our mean, we found our variance. Our variance was 1089, and then we found our standard deviation, and then we used Chebyshev's to help us out. Adam, it'll be recorded and it'll be put on the home page of our D2O page. I'll put this up there. So if for some reason yours is lagging or you're having bad internet, you can always watch it later. And the nice thing about being able to watch it later is you can always put it on 2 times speed. And then I'll be talking like this, I'll talk really fast, but you can still understand what I'm saying maybe. Maybe I need to be on 2 times speed all the time anyway. Okay, so now let's do this one. And then I'm going to have a challenge for y'all today. All right, the doctor expects 1 out of every 5 patients they see to have high cholesterol. If the doctor sees 25 patients in a day, how many patients would be expected to have high cholesterol? So, if I want to know that expectation, or on average, how many we have, Zoe, it depends on what the question's asking. So you have to really read to find out what it is that you want. Do you want the expectation? Do I want standard deviation? Do I want the variance? So you need to know the difference, and then you need to be able to answer the actual question that's there. So this is going to require you to actually, read and think about that question. So not every problem will have all 3 answers. It's going to depend on the question. Okay, so back here, is this a binomial? Can I use this formula? Or, just what makes sense? It's binomial to me. This expectation just makes sense. Good, Adam. It just totally makes sense that 1 out of every 5 patients they see have high cholesterol. Then how many do we expect to have high cholesterol? Well, it's just 1/5. 1 out of every 5 patients out of 25. So my expectation is just going to be the number of trials times probability. And yes, it is binomial because we have high cholesterol or we don't. And now Adam's on the road to health. Don't let this pandemic mess you up, Adam. You keep working out somewhere in the house, I don't know. Lug some boxes around or something, that you keep that going. You go, boy. Okay, so now so it's have high cholesterol, don't. My probability remains the same of 1 out of 5, and then my fixed number of trials is 25. And Bo, that's exactly it. The setup there is 25 times that probability for success of 1 out of 5. And y'all have already found it for me. That mean, or my expectation, is that 5 of my patients have high cholesterol. What is the variance? What is the variance? Who else is up at 5 a.m.? Eve and I were almost up till 5 a.m., but not quite. We went to bed before then. Or at least I did. I don't know about Eve. She had some chores to do. Okay, so variance here. I'm going to take my mean, and I have to multiply it times my probability for failure. So in this case, what is the probability for failure here? So if 1/5 is my probability for success, then 4/5 is that probability for failure. So now I just multiply that. Well, this 5 and that 5 become 1, and I'm just left with the 4. So my variance is equal to 4. Now let's find the standard deviation. So the standard deviation, we just take the square root of that, and our standard deviation there is 2. So on average, we expect 2 from the mean there, that distance from the mean. There's our standard deviation. Okay, so here's the question. I'll write it out so that you can kind of see what at least 75% of the time of the days the doctor should see between what two numbers of patients with high cholesterol? Cholesterol, can't spell that. That's kind of poorly worded, but it's kind of the idea. So at least 75% of the days, what's the range of patients we expect to see with high cholesterol? So notice I might just ask this question, but in order to answer this question, the first thing you have to do is find the mean, and then find the variance, and then find the standard deviation in order to be able to answer that question. But if I just ask you what is the expected value, or what is the mean, then you could just stop there. So in this question, my answer is just 5. For this question, I just do n times p, so I just get 5. So to answer your earlier question, Zoe, if I ask this question, my answer is 5 and I'm done. If I ask this question, I have to go through this whole process, plus now I have to do this and say, well, my mean is 5, so I'm adding that 2, I'm adding that 2, I'm subtracting the 2, I'm subtracting the 2, so at least 75% of the time, I'm going to get between 1 and 9 patients a day that have high cholesterol. So again, if I'm doing something where all of a sudden I'm getting a lot of patients every day, if I'm getting another one, a lot of patients every day, then I start wondering, what is it that moved into town that's given my constituency high cholesterol? Or what is our town doing different than some other town that is giving our town high cholesterol? Or maybe I want to do this. Maybe I want to lower the high cholesterol in my town. So I send out a campaign and I start telling people what to do to help lower their cholesterol. Exercise every day, stay away from red meat, don't eat carbohydrates, whatever to help you lower your cholesterol. So then I want to see, is my campaign working? Is this working? Have the people lowered their cholesterol? Then I could use this, and if all of a sudden, I'm getting something weird on the low end, then I can go, oh, it really is helping to, or maybe, it seems to be helping anyway. So, okay, so that is today's lesson, the expectation, the standard deviation, and the variance. So you did the first 10 of the homework yesterday where you used the binomial distribution formula to help solve that, to find the probability of something happening. And the last 10 today, there may be some of those probabilities mixed in, but most of these on the last 10 of your homework are going to be using the expectation, finding the expectation, and the standard deviation and the variance. So it won't be so bad. And the Chebyshevs, maybe I ask you some Chebyshev type of questions. Okay, now I'm going to give you a challenge, and I'm going to give you something that might help us with this whole combination thing. All right, so I'm going to teach you about something called Pascal's triangle. So let me erase all this and show you Pascal's triangle. Uh-oh, nah, it won't be too bad. Well, maybe it is, but no, yeah, maybe. Okay, so, yeah, Adam's got this down. He already knows it. Okay, so let me just show you with Pascal's triangle. I'm going to start with a coin, and I'm going to flip a coin. So, here's my coin. I'm going to flip that coin, and when I flip the coin, I could get either a heads or a tails. So, I have these two outcomes. I could get a heads or a tails. Every time in this that I flip a heads, I'm going to go to the left. And every time I flip a tails, I'm going to go to the right. Okay, so now I have those two options. And we've made these trees before, right? Where we said heads or tails. And then we said, well, if I flipped a head on the first one, so here I hadn't flipped any. There were zero flips. Here I flipped it one time. And when I flipped it one time, I had two outcomes, two possible outcomes. And those possible outcomes, well, I had, you know, this, I could get one head or I could get one tail. Okay, now I'm going to flip it again. I'm going to do a second flip. In which case, if I flipped a head on the first time, then I could get a head and a tail. So I could get a head. I'm going to go to the left here for a head, and to the right there for a tail. If I flip a tails first, then I could get a heads, which goes to the right, to the left, or a tails. Now, think about our tree for just a minute. When we did our tree, and let me just kind of show you on the tree what I'm doing, but I'm going to get rid of certain things. You remember doing this tree where we've got heads and tails? Okay, so we have one heads, one tails. Here I've got heads, heads. Here I've got a heads, tails. Here I've got a tails, heads. And here I've got a tails, tails. Notice that I just have one of them that are heads, heads. So there's one arrow going down to that heads, heads. But there are two different ways that I end up with a heads, tails. So this one I went heads, tails. That was one way to get there. Another way was to get this tails, heads, tails, heads. There's two different ways. And that's what this is representing. I flipped a heads and then a tails. Or I could flip a tails and then a heads. So there were two different ways to get there. On this last one, there's just one to get here. So I could keep going with this tree, or this Pascal's triangle also helps me see the same thing, maybe a little bit more organized. I don't know, maybe not. By the way, how many potential outcomes were there? There were 1, 2, 3, 4. There were total of 4 possible outcomes there. Okay, I'm going to do the same thing. I've now done a heads and a heads. I'm going to make this go to the heads or to the tails. Here I did a heads, a tails, and a heads. So notice this direction, I got a heads and a heads, 2 heads and 1 tails. This way I also got 2 heads and a tail. So there were, since there were, there's 2 arrows coming from that. There were 2 ways to get from that. I'm going to make it 2 ways going there. And 1 coming from there. I don't feel like I'm doing that great a job, but maybe you'll get the idea from it. Staying up too late last night. My explanation's not great. But we might should have made the tree out first and it would have made more sense. Okay, here I've got 2 arrows that are going to come that direction. So if I flipped that tails, there were already 2 ways to get there. Well, then this is giving me 2 ways to get here, plus another way to get there. So that gives me a total of 3. So if I flip 3 flips of the coin, which we've done before. We did it and we made out the tree before. And every time we did that, we had 3 kids on one of our examples where we made the tree. Or the arrow, remember the archer who shot the arrows at the target, and he did it 3 times. So we made that tree out over and over and over again. So in this case, I'm just doing 3 flips. Always there were 8 possible outcomes there. Notice that I'm going to have 8 possible outcomes. 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes there. What about if I do 4 flips? Well, this way, I still just have one arrow coming down that direction. Here I've got one arrow plus these 3 arrows coming there. Makes a total of 4 arrows. This direction I have 3 arrows coming from here and 3 arrows coming from there, which makes a total of 6 arrows, or 6 possible ways. Here's 3 possible ways coming that way, 1 possible way coming that way, gives me those 4. And then that direction, I have a 1. Now there's a pattern that's happening here. Notice that really all we're doing is taking and adding these 2 numbers. I'm just taking 1 plus 2 to get that 3. I'm just taking this 3 plus 3 to add that 6, to get that 6. But this is kind of the idea, that tree that we made earlier in the year, or earlier before spring break, told us the total possible outcomes. And this does kind of the same thing in a different, just a different visualization of it. Notice if I flipped it 4 times, I would have 1 plus 4 is 5, 11, 12, 13, 14, 15, 16 different flips. So this is Pascal's triangle. Normally, we don't go through all the little arrows part. You just write it out like this. You start with 1 on top, which is a little bit weird because there's nothing in that. You know, that's for 0 flips. But we start with the 1 on top. Then we say this is 1 and 1. And then I just start adding. Always, every time, I'm going to come down with a 1. I add these together. 1 plus 1 gives me 2. And over here I get 1. Same thing. Bring that down. Add these together. 1 plus 2 is 3. 2 plus 1 is 3. Bring that down and I get 1. Bring that down, I get 1. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And then you always end with a 1. Keep going. I'm going to do just a couple more rows. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. And 4 plus 1 is 5. And then you always end it with that 1. One more, I'll do one more row. This is 1. 1 plus 5 is 6. 5 plus 10 is 15. 10 plus 10 is 20. 10 plus 5 is 15. And 5 plus 1 is 6. And then there's 1. Okay, we say within this triangle that this is the 0th row. Which, you know, we didn't flip it any there. So that's where that 0 comes from. This one is the 1st row. This one is the 2nd row. Etc., etc. So there's the 3rd row, the 4th row, the 5th row, the 6th row. Then this entry out here is the 0th row. Entry. 0th column. This one is your 1st. So all along here is your 1st entry. This one is your 2nd entry, etc., etc. Okay, so here's what I want you to do. I want you to start. Notice this guy right here is on the 0th row and the 0th entry. Here's what I want you to do. I want you to find for me this combination. 0th row, 0th column. And tell me what you get. Then, I want you to find the 0th row and 1st column So 1, he's on the first row and 0th column. So do 1, choose 1. 1, choose 0. And then here, we're still on the first row, but we're on the first column. And find out what you get there. Then I want you to do second, choose 0, because it's the second row, 0th entry. Then I want you to do second row, first entry. I want you to do second row, second entry. And I want you to continue this to the 5th row. Then, I want you to use words to explain how to get using the Pascal's triangle. Okay, so this is your bonus. You're going to do this. Bonus opportunity. You're going to do this right here. Continue to the 5th row. Then I want you to use the words to explain how you get the answer to 8, choose 3 using this this Pascal's triangle. If you make a video of your explanation and upload it somewhere where I can see it, upload it where, send it to me. Mr. Simpson, how do you have them do their videos? Where do you have them send it so that you can share them? If they can do a video of it, I'm going to give them extra points for doing the video. So here's a bonus opportunity. Do this, explain using words, and then give me a video of that explanation. So just doing this part is going to be +5. Then if you can give me a video of you doing it, upload it, and Mr. Simpson's going to upload it to YouTube. If you can upload a video to YouTube, I'm going to give you an additional +5. Okay? So there's a potential +10 right here, sitting right there. All you have to do is do this bonus, and then upload me a video of your explanation there of how you can get to, or choose your own. It doesn't have to be 8, choose 3 so that we're not all the same. But there's 8, choose 3, whatever, that works. So Mr. Simpson's telling you exactly what you're doing. You're going to upload it to YouTube, send us the link, and send a note that lets us know that the link is safe, so that we're not we don't click on anything that we don't know is safe, So we can't upload it for you. So you see what Mr. Simpson's saying there in the chat. I'll give you till Saturday Eve to do it along with the homework. So you got till Saturday at midnight to do it just like with the homework. All right? So there's your bonus. Bonus opportunity. You got this. Oh, sorry. Sure can. I can move. So that's Pascal's triangle in a brief summary. I might also, Mr. Simpson, I don't know if he gave away the answer or not. Did you in your video, Mr. Simpson, give away this, or can I share your video with them to help? If not, I'll do it later. Okay, you guys got this. Great, Adam. Enjoy your boys. And today's homework will fly by quick, so get on right now. Let's do your homework. And then you can get your boys and go spend some time with them. Go fishing. I bet the fish are biting today after all that rain yesterday. So, you can do this. Oh yeah, I'm going to upload this, Ankara, to the to D2L right after this, and so it'll just be on the first news item in content, and so you can just look under that news item, and there'll be a link to link it to this video, and you can skip right to where it is and pause it. And that's the nice thing about these YouTube videos, is they record, and so then we've got a recording of them, so then you can just pause it and you'll have it. So hopefully. Okay, so y'all have a great afternoon. Come join me on Discord. I'll be there right now, and hopefully these last 10 won't take that long to do. All right, Math Made Simple at Simpson Math. Thanks for watching. See y'all later.